Hello, this is Friday. Yes, we actually made it to the end of the week, and it's February 5th. This is ECE 637, Digital Image Processing 1. And today I think we're going to try to finish up the material for tomography. I don't know if there's any questions from the studio audience. How's everything going? The labs? I think one of the labs is due today, is that correct? Is that lab okay? Did anybody look at the lab following? By the way, we posted a revised version. So there's two kind of web pages for the lab, just to remind you. One is the sort of old legacy version of the labs, and the other is the new and improved version of the labs. So hopefully we'll get all the new and improved ones done. But there may be some so like you can the lab 3 is posted for the new and improved version. Has anybody started it yet? Maybe. No. Okay, that's fine. But I was just wondering if you run into any problems, let us know because of the revisions. Hopefully, we'll stay ahead of the curve on that. But if there are no questions, I'll start launching into the material on tomography. So yes. So the idea is that the key idea of the key to reconstruction is the Fourier slice theorem, which is mathematically represented like this. That's the Fourier slice theorem. But the idea is that, and oh yes, this was my. I like this slide. This was the key idea that you plot the data. So what you do is for each projection is a 1D thing, right? As a matter of fact, I have an example here in the back. So maybe I'll do a little bit out of order so you can see how it works. Okay, so here's the example. There's actually a MATLAB example on the web page. You can run this yourself because it's a MATLAB script. Maybe we should do it in Python. We should convert it to Python in keeping with the spirit of the class. But we have, okay, so it looks blurry for some reason, but this is like what they call a phantom, a digital phantom. And their real phantoms are actually physical objects that they put into scanners that have known geometric properties, so that they know what the reconstruction is supposed to look like. They use it for calibration and so forth. So this is like a digital phantom, and it has two ellipses in it. And obviously, this ellipse is brighter than that, so that it would represent a more dense material. Remember, brighter is more dense. So something that's kind of interesting is that when you take a planar X-ray, like a chest X-ray, what happens is that the dense things are dark. No, I guess it depends on whether the film is a negative, but the dense things have fewer photons that hit them, and the less dense things like air have more photons. But you have a contrast reversal that occurs because of the negative log I talked about. And so what ends up happening is that black represents zero density. It's actually zero. So what we're plotting here is something proportional to density. So this is 0, and then this is a larger value. So that the integrals through this thing, you're integrating with a larger function, but the thickness of the thing is less. So the integral may not be, like the integral through this thing might be larger than the integral through that because this is smaller and that's bigger, but this is brighter. But if you go in the other direction, the integral this way, the integral through that is going to be larger than the integral through this because they're about the same thickness, right? But this is a lot less bright, okay? So if you do that and you can do a projection at a particular angle. So let's say you go this way, you integrate on long rows, you get a projection, right? That's going to be a 1D function. You plot that 1D function, And then you maybe move a little bit, and you plot the next 1D function at a slightly greater angle until you get to 90 degrees, and then you're projecting this way, and you come all the way around here. Once you come to 180 degrees, you don't bother going any further because this projection is the same as that projection. Do you see that? So it has the same information. So if you plot it, it looks like this. This is a sinogram. I was going to give you a sinogram of a real object. I have to see if I can find this, but this is a synthetic. At least gives you the idea. So the idea is that when you're, so this is the zero angle. So it's zero angle by convention for this particular case. That was integrating straight down. So you get two things, right? And if you look at it, let me zoom in. You look at it over here. So if you do that, you might see that, okay, well, maybe it's a little hard to see. But well, you certainly see this blob. What you may not see so well is there's a second little shadow right there. Do you see that? So the second shadow is from the integral, is the integral through this object, because the integral through that object is much less than the integral through this object. Even though it's brighter, it's smaller, right? So it's the product of the brightness and the length. So, you know, if you have, intuitively, for the transmission case, the photons, it's harder to penetrate a thicker object. It'd be like if you're trying to shoot a bullet through a concrete wall. If it's like a 1/4 inch thick, it might go through, but if it's like 3 feet thick, it won't, right? So that's what happens. And now if you rotate to 9, okay, so you start here, and then you go to here, but you get to here, what happens is that this thing's kind of all spread out, but that's sort of concentrated. So that's what you see over here. That it's the brightness of this thing should be actually constant, except for it's on a pedestal here. So I guess it also could be a kind of a visual illusion. But anyway, at 90 degrees, this is angle in degrees. At 90 degrees, you can see the small object, but the large objects is sort of dispersed because it's wide. And then the way you usually plot sinograms is like this, actually. I mean, conventionally. So what you'll do is, if you have objects in the image, they'll plot out sine waves. And you can see this plots out a sine wave, right? So that makes sense. Okay, now what we're going to do is, okay, now the thing is that if you take this sinogram function and you take its Fourier transform along rows, okay, so you take the 1D Fourier transform along the rows, you'll get a new 2D function, okay, which is a function of angle and frequency. And that function is here. Okay, I'm not even going to plot it, but it would be some kind of function, okay? Now, here's the trick. So what happens is that you take the Fourier transform this way, and then, what happened to my, oh, yeah. Then what happens is that, so this is angle theta, right? And then this is no longer displacement because you took the Fourier transform. So it's a Fourier transform. So that's the independent variable for frequency. I'm using a rho. So you take the Fourier transform along each of these lines, okay? And that's this thing here. Now what you do is you do a polar to rectangular coordinate transform. So over here, say, this is 90 degrees. So this is 0 degrees. So what will happen is, like, you'll be here, I don't know, like here, you take this thing, right, and you plot it like this. And that angle, theta, corresponds to this angle, theta. Okay? Does that make sense? And then you take the next point. Unfortunately, we don't have an infinite number of colors. And you have another one, and then that's the next angle, right? and this is theta here. Does everybody get that? So you take this thing here and you plot it in rectangular coordinates, right? Then you take, so this thing here is the amazing thing. So this is the polar coordinate transform of this, but it turns out that this is f of uv. It's the 2D Fourier transform of the original image you wanted. So if you want to recover the original image, then what you do is you take the 2D inverse Fourier transform. Let me zoom out a little. Of this. So this would be a continuous space Fourier transform inverse. And then you get your object back. Okay? So that seems pretty simple. You go, oh, okay. So this is how I can do reconstruction with the Fourier slice theorem. I can take the image, okay? Okay, so first of all, the first step I do is I take the image and I take its projections. Now, the way that's done is normally not with a computer because that's the actual measurement process. So you have some object and you measure its projections. So that's where you get these projections, okay? And that measurement process is different for different kinds of instruments. But then once you have these measurements, you take the Fourier transform along the rows, okay? Then you plot it in polar coordinates, and then you take the inverse 2D continuous space Fourier transform, and you get the object back, okay? Now, there's a problem with this, which is actually not a huge problem because the truth of the matter is this is actually how it's done in many cases, right? But there is a problem, which is that doing, okay, in discrete space, if you try to plot this, it's a little tricky. It's hard to take these values and plot them into polar coordinates because they're not, the samples aren't going to fall on grid points, right? Do you kind of see that? We haven't talked about 2D sampling yet, but you know, if I try to plot polar coordinate values on rectangular coordinates, they won't fall on the grid points. So, like, what are you supposed to do? Well, the answer is that what you can do is you can do interpolation. You could do you could either take these points and sort of, you know, map them sort of the closest point on the grid point, but that's really rough. And that'll give a terrible result. So there are methods where what you can do is, the other way you can go in the other direction. For each of these rectangular grid points, you can interpolate the point in polar coordinates that corresponds to it and do it that way. But you have to do this transformation, and it's a little tricky. So that tricky transformation is basically, we'll talk later in the class about sampling and interpolation. It's a nasty sampling and interpolation problem, but there's been a lot of progress made on that in the last, I don't know, 10 years, maybe longer. So, and then you can take the inverse Fourier transform. The alternative is to try to take the inverse Fourier transform in polar coordinates, and that's hard because the 2D FFT works because it's on a rectangular grid. If you try to take the FFT and convert it to a polar grid, it no longer has the properties it did, and it's not fast. So the computation would be really high for doing direct polar inverse, okay? So that's the problem, or the challenge, but people do still solve things this way. So, but this is, I like this diagram here. So we have, this is the projections we directly measure. We measure this with, say, transmission CT. Then we take the Fourier transform along rows. We get this. Then we plot it in polar coordinates, and we take the inverse Fourier transform. Okay, so that's how you go. But the other thing, and that's the Fourier slice theorem. And the Fourier slice theorem is very simply stated, but you have to, it may be a little abstract, is that if you take the continuous time Fourier transform of the projections, so these are the projections, that you get this. And if you take the continuous space Fourier transform of the image, you get that. And these two Fourier transforms are related through a polar coordinate transform. That's the whole thing, okay? Now, you might say, okay, we could prove it, and you go through the analytical proof. but I won't do that. I'll let you look at it. But instead, let me answer the question you haven't asked me, which is, well, give me a good idea why it is true. I mean, it doesn't seem like, it seems surprising that that would be true. Okay, I'm glad you asked that question. Here's why it's true, intuitively speaking. So you have some object, X and Y, right? And you have an object. Okay, that's the object, okay? Now, if you integrate, say, vertically, so then you get a 1D function. So this is going to be P0, 0. Oh, I keep wanting to make a theta. My brain wants to make a theta there. 0 R. So this is the projection you get if you integrate down like this, right? So you get, okay. So that's going to be some kind of function. I don't know. It's going to look like this. Like that, okay? Let's say that's what it looks like. Now, okay, what you're doing here is you're computing the sum or the integral along vertical lines, right? Now, if you had, this is such an intuitive idea that I really want you to understand it. Once you get it, I think you would just say, oh, that makes sense. Okay, so let's say you have, oh, this is an important thing we learned in this class. F of t. There's a couple of things that every student in this class must know by the end of the semester if they want to pass the course, okay? Or at least if they don't want me to be horribly disappointed, okay? That if you have some function f of t, okay, and then it has a Fourier transform f of omega, or f of f, I guess. Oh no, let me make it a g so as not to create ambiguity. So this is continuous time Fourier transform, okay? So this is, okay. Now, the value here, so that now there's, okay, I can't really plot g of f because it's complex value. Okay, but this value, g of 0, what's g of 0 equal to?
Absolute sum of all the points in G.
Yeah, except for instead of sum, it's integral. So if I look at the Fourier transform integral, right, it's g of, I think g of f is equal to the integral from minus infinity to infinity of g of t times e to the minus 2 pi ft dt, right? So if f is 0, what's e to the minus 2 pi ft is 1, right? So g of 0 is equal to what? It's equal to the integral from minus infinity to infinity of g of t dt, correct? And what's that intuitively? Just like, what are the words to describe what that is? Tell me in words what that is. It's the area under the curve, right? It's the area under the curve, correct? Does everybody know that? That's obviously the area under the curve. I'm oversimplifying slightly because if the thing went negative, then it wouldn't be, it would have to define, depending how you define area. So you would subtract the part that's negative from the positive part. But it's the area under the curve, right? It's the integral from minus infinity to infinity of g of t dt. So here's the thing that everybody in the class should know at the end of the semester. What's g of 0? What's the 0 frequency represents the what? Say it. The 0 frequency is equal to the, that's the 0 frequency right here, g of 0. And g of 0 is equal to this, right? So the 0 frequency is the area under the curve, okay? Let's just say that for the purposes of Pavlovian training. Okay, so 0, g of 0 equals 0 frequency. Oops. Equals the integral from minus infinity to infinity of g of t dt equals, what is this? The area under the curve. And I also refer to that as because I'm trained as an electrical engineer. It's like once you've trained as an electrical engineer, you're always an electrical engineer for the rest of your life. It's a sad thing, but what are you going to do? So what is it? It's called the DC, which is kind of a ridiculous name because what the heck does current have to do with it? But it's the direct current, okay? Because this is like burned into the brains of electrical engineers because of the fight between Thomas Edison and what was the other guy's name? What's his name?
Westinghouse?
Oh, well, him too. Yeah, Westinghouse. But the other guy was. We have his bust in the hall in MSCE. It'll come. Nikola Tesla. Tesla, right? They fought between DC and AC. So now it's kind of burned into everybody's brain for all posterity. So what is the DC component? It's the area under the curve, and that's the 0 frequency, right? Super important. That happens for discrete time too. So when we design a filter, if we want to preserve the DC component, which we often do on images because you don't want the image to become brighter or darker, you want to make sure that the impulse response sums to 1, okay? Right? One sums to 1, okay? So that's 0, that's the 0 frequency. Okay, you got that now? Okay, so I digressed a little bit, but let's get back to this. So now what happens is that when we integrate vertically, what are we computing? If we integrate vertically, what's the interpretation of that function? So this is a function of f of x and y. And now we're integrating over y. Right? And that's the projection. That's what the projection is. We integrate over y. So we're computing the, what's the words that, we're computing the, it starts with the word area. Okay. Okay. Just say it to make me feel good, okay? Please, as a personal favor, we're computing the area under the curve, right? You're computing the area under the curve, but now for each x, you're doing that for y, right? So what has that got to be equal to? Well, it's a 2D Fourier transform. So it's f of u and v, right? V corresponds to the frequency in y. So it's going to be the DC component because it's the area under the curve, right? So what do I write here? Does anybody know? 0. Voila, right? Do you get that? So here's the Fourier slice theorem is really super obvious once you understand that, because you'd say, well, that's obvious. Duh, you know? Okay, I shouldn't say that, right? It's not nice, but okay. Obviously, because if I have some object like this, right? Right? And I project it, I get, you know, the projection like that. Then if I take the Fourier, so what this is doing is it's evaluating at the 0 frequency. So what ends up happening is if I take the Fourier transform, continuous time Fourier transform, right? I get now, I get, this is the, so this would be f of x, y. And this is f of f. Oh, let me make this a g. so I don't keep having this problem. F of oh, I'm sorry, G of UV, right? So the Fourier transform is going to be the value of G of UV along here. Right, because this is U, and this is V. So this corresponds to V equals 0. So what happens is that if I take the Fourier transform of the integral, if I integrate first, I'm only getting the DC component along V, and I take the Fourier transform, I'm going to evaluate the 2D Fourier transform along this line, okay? Now what happens is that if I take the object and rotate it, well, this will rotate and that will rotate. So I'll now get the 2D Fourier transform along. So if I take so this is the object now, okay, and this is X and Y, and then I rotate it like that. Now what will happen is that in U and V, I'll get the Fourier transform along the tilted curve. Right. Do you see what I'm saying? So everything just rotates. Maybe that picture's not so great. So that's the intuition between the radon. That's the intuition behind the Fourier slice theorem. That when you take these projections, you're effectively computing the DC component. So you're evaluating it along a line, then, the Fourier transform. And then when you rotate things and take the projection again, you evaluate it on a rotated line. So you get all the rotated lines to the 2D object's Fourier transform. And from those, you can reconstruct the object. Are there any questions? Does that make sense? The beauty of this is you can watch this video again if you choose. So, okay? So that's the upshot. Now, and then this shows the picture. So this is the alternative proof. It just says, okay, this is a projection at 0 angle. This is the Fourier transform of the projection at 0 angle. And then I just do a few simple manipulations, and I see that this is the Fourier transform evaluated, the 2D Fourier transform evaluated at an angle of 0. If that's true, then by the rotational invariance of the 2D Fourier transform, then a projection of the rotated object will be will evaluate the 2D Fourier transform along a rotated line. Okay, so that's why one is basically the polar coordinate representation of the other. So what ends up happening is that this just shows that this is the transformed projection at each angle. So for each angle, you take the Fourier transform and you plot it in polar coordinates like this, and you get the 2D Fourier transform. Okay? Are there questions about this? Does this seem reasonable? So now that's fine, except for this issue that I pointed out, which is that it requires that you interpolate, you convert from polar to rectangular coordinates, and that's difficult. So, yeah, I guess it's this diagram here. The problem is going from here to here is tricky, because you either have to do a 2D Fourier transform in polar coordinates, and that's hard because computationally it's no longer n log n, it's n squared, or you have to interpolate from polar coordinates to rectangular. And whenever you do interpolation, there's always error, so it's never perfect, right? There's always going to be issues, but there's modern interpolation algorithms that are pretty effective that people use. And so a lot of people still do this, although years ago maybe not so much. But the other approach is a thing called convolution back projection. So in convolution back projection, basically the idea in convolution back projection is you want to do the polar coordinate inverse Fourier transform. So you say, okay, well, can we just evaluate the 2D Fourier transform in polar coordinates? And sure, Yeah, I mean, you could do the standard calculus, multivariate calculus thing where you change your coordinate system to polar coordinates and try to do the integral there and see then if it works out. So if you try this, so this is the 2D inverse Fourier transform. But now what you do is you convert it to polar coordinates. And f then in polar coordinates, f is p. So remember, p here is the 1D Fourier transform of the projections. So p is what we get by taking the Fourier transform of each projection, the continuous time Fourier transform. And then this is the polar coordinate transform of this. So you replace x with x cosine theta and y with y cosine theta. And then you replace these differential terms with this is like, you remember this from multivariate calculus, right, in your sophomore year or freshman year. And now what happens is this is integrated from minus infinity to infinity and 0 to pi. You could have done this from integral from 0 to 2 pi and then 0 to infinity. Either way, you cover the entire area of the plane. But I chose to do it from minus infinity to infinity. So r here, rho, is going from minus infinity to infinity, and theta is going from 0 to pi. And then you make some substitutions. I'll let you look at this because okay. And you get this expression here, okay? Now, there's G here is defined like this, okay? Hold that thought. And now, okay, so F is, okay. Yeah, I'm missing something. Okay, it's wrapped around the page. So, okay. There's really two steps here. Okay, so if you interpret this mathematical formula, if you define this expression in brackets as this thing G, then G looks like the inverse Fourier transform of P. P was the Fourier transform of the projections. So if you take the inverse Fourier transform of the Fourier transform, you would just get the projections back. But you don't get the projections back because you're multiplying by rho. So what does rho look like? Remember, rho is frequency. So it looks like a filter you have where the transfer function of the filter is the absolute value of rho. So it's like you have a filter in the frequency domain. This is rho. And it's a real value filter, and its frequency response is like this. So this is magnitude of rho. Now, if you continue on to infinity, the magnitude goes to infinity. So you can't take the inverse Fourier transform. Okay, this is like multiplication in frequency corresponds to convolution in time. So applying this filter to the frequencies is equivalent to convolving it in time, except for I can't take the inverse Fourier transform of this because it goes to infinity. So what I do is I make the assumption that the signal's band limited to some maximum frequency, we'll call it rho 0, and we cut it off. All right. Now I can take the inverse Fourier transform of this. Working it out analytically isn't too bad because I know what the inverse Fourier transform of a rec is. It's a sinc. And then this thing looks like a triangle, and the triangle also had an analytical form. The triangle is formed by the convolution of two recs, so its inverse Fourier transform is a sinc square. So this expression is going to look like a sinc. Its inverse Fourier transform is going to look like a sinc minus a sinc squared. So I can get an analytical expression for that. And then what ends up happening is that what it really is G of theta, G theta of R, where I wrote, of R. Oh, that's a typo. Oh, well, I'll take care of that later. Is equal to H of R convolved with P theta of R. So these are the projections, And these are the filtered projections. So what are the filtered projections? What is the filter? H. Well, the form of the filter, let's jump ahead, looks like this. That's the analytical form, I told you. It's a sinc minus a sinc square. And these are all the correct scaling factors to make it come out exact, okay? So once you have the filtered projections, then what do? You plug it into this thing, and that expression looks like, if you just do the math, you do the algebra, it looks like this. So you take the filtered projections and you plug them into this expression here. So what is their filtered projections? The filtered projections, okay, well we know, okay, what is this thing? This thing is called back projection. Back projection is the adjoint operator to projection. We know what projections are. Projections take the object and we do integrals along lines, right? In a back projection, whenever you take the adjoint of an operator, the domain, so you have an operator, and the operator, hold on. Adjoint is a fancy name for transpose, first of all. So when you have like y equals ax, and everybody knows that the adjoint is the transpose, right? So the adjoint, you say, oh, a transpose y equals what? Z, something. The point is this. This is, A is an operator. It takes inputs from its domain and produces outputs in its range. The range and the domain may not be the same. They are the same if A is invertible and square. Well, it's got to be square if it's invertible. But if it's not square, then the range and the domain are different. They're actually different dimensions. So the range and the domain are not the same thing necessarily. And in the case of the tomography, the domain of the operator is images, and the range is sinogram. So this is an image, and this is a sinogram, right? The adjoint or transpose of an operator goes in the opposite direction. So this, this is a domain, and this is range. So this is A, and A transpose goes the other way. Now, because of the fact that the transpose or adjoint goes in the opposite direction, we tend to confuse it with the inverse. The adjoint is not the inverse in general, although it may be the inverse, but it does have the property that it goes from the range to the domain, okay? And the back projection is the adjoint operator for the forward projection. So it takes the sinogram data and turns it into an image. It's not the inverse, but it is the adjoint, right? So now, in order to get some more intuition as to what the back projection does, so if you have a projection, so this is P theta R, and let's say the projection looks like this. It's a point like that, right? For some theta. Well, what ends up happening, this is X and that's Y. So when you do the projection, you integrate along lines. When you do the back projection, you take the value and you smear it back along those lines. So the way I like to think about it is like you had a paintbrush. And the paintbrush, the amount of paint at each point would be associated with the value of the projection at that point. and then you smear the paintbrush over it, okay? Does that make sense? So the back projection sort of goes in the opposite direction. The adjoint is like if you reverse the flow in a graph, okay? So to recap, what's the summary of the convolution back projection? You first measure the projections. The projections are measured using some physical process. Then you filter the projections. You filter the projections with this special filter, which I told you is, this is its form. It's the difference between a sinc and a sinc squared, okay? And its frequency response is this, okay? So it's sort of a high-pass filter. It accentuates the high frequencies, right, because of its frequency response here. And then once you have the filtered projections, you back project the filtered projections. Now, like I said, there's a tendency to feel that adjoints are inverses, and they're not. The adjoint is the inverse only when the transform is orthonormal. In the special case of orthonormal transforms, the adjoint and inverse are the same. But in general, the adjoint and inverse are different. So, but there is a kind of sense that it kind of reverses the process, so it should kind of get you back where you started. But it doesn't do the inverse. But what's interesting is that for the radon transform, if you filter the projections, then it does become the inverse, because it reconstructs the image from its projections. That only works if you have an infinite number of projections and the signal's band limited. Okay, but it does work in that case. So that's kind of interesting. And the other thing, this is a pop quiz, okay? Now, we spent all this time talking about, this is the impulse response, right? H, and that's its Fourier transform, right? What's the DC component of this filter? This is like a Jeopardy question. Da, 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 da. What's the DC component? 0. Why? Because this is equal to 0, right? So what's the area under the curve for this function h? 0. My questions are so easy. You can actually answer them without really understanding the answer because you just say 0. Okay, so that's it, right? So if we plot that function, it looks like what? Oh, and this is, well, I'll plot it in just a minute. So this is the back projection. Again, it's smearing back along the lines, right? Now, in practice, you can't take an infinite number of projections because the computer can't store them. So what you end up doing is you take a finite number of projections. So you take discrete projections at discrete angles, right? So if you have, I don't know, you might have 180 projections over pi angles. So then the projections would be spaced by 1 degree. So if you do that, you're approximating the integral by a sum. So then what happens is you have this sum, but you have to multiply by this appropriate factor. It's sort of like the size of a trapezoid to correct it so that it's equal to the integral. And then the question becomes, an important question becomes, how many projections do you need? How many projections do you need? Well, the answer, there's a few different ways of thinking about it. But if you have an, okay, this is y, this is x. Now, if you discretize the image, then you have discrete pixels. We'll be talking about that later. So if it's n by n is the image, okay? And then intuitively, if you take a projection, say, approximately the number of samples you have in the projection, in the parlance of tomography, you would call this the number of channels. So usually the number of channels is about the same size as the number of the size of the image. So it's n. There's some pies floating around there because you have inscribed circles. What really happens is you have an image. Usually what happens is you only try to reconstruct a circle in the image because of due to the symmetry. So this is all 0. So really you don't have n squared unknown pixels. You have something less than n squared unknown pixels. And then you have, you take the projection then will have n pixels in it. So you have n measurements per projection. And so you have roughly, the inscribed, I actually should know this. So the number of pixels is equal to, it's going to be n squared, but it's not quite n squared because the area of the inscribed circle is less than n squared. What is the area of the inscribed circle? Does anybody know? I should know this. Shoot. I feel like I'm going to have to do it real fast. So it would be like 1/2. What's the area of a circle? Pi r squared, right? Okay, so it's pi 1/2 squared. Did I do that correctly? So it's going to be pi over 4, right? Pi r squared. Is that correct? Oh no, the area of a, what's the area of a circle? Oh no. I'm assuming this is 1. Right. So I'm just trying, because then the area of the square is 1 in that case, and then the area of the inscribed circle is pi over 4, which is less than 1, right? So the number of pixels that are unknown is pi over 4 times n squared, approximately, right? So then the question is, how many projections do we need? Well, you need as many data points as, in order to make the problem invertible, you should have as many measurements as unknowns, right? So, number of, oh God, this is a mess. Number of projections is 1. So the answer is going to be, I'll write it out again, but I just thought I'd write it here so you can see this, is 1. It's going to be, the number of measurements is pi over 4 times n squared, right? Divided by n is equal to pi over 4n. So you need pi over 4n projections. So if you're trying to reconstruct an image, which is 1,000 by 1,000, you need actually more than that. You need at least roughly n projections. So if you have a 1,000 by 1,000 image, to reconstruct it, you need 1,000 projections. So the number of projections goes up pretty rapidly with the size of the image, is my basic point. Okay? So that's interesting. Okay, now here's the example. We're running out of time, but I think we'll finish on time. So here's the example. So those are the projections. I already argued about why it looks the way it is. Normally the sinogram would be displayed this way, but we're doing it this way. Okay? Now if you take, that's the example of the filter. This is the filter corresponding to a frequency response that looks like this. Okay, it's the difference, and you can see if you zoom in here, the area under the curve looks like it's 0. So if you sum the impulse response, it comes out to 0 because the frequency response at DC is 0, right? So if you filter that, what will end up happening? That looks like a high-pass filter. So you accentuate the high frequencies, okay? Okay, so it makes it edgier. So when you back project that, if you back project just one projection, you get this, okay? It doesn't look very good. If you back project 2 projections, you get this. If you back project 4 projections, you get this. If you back project 8 projections, oh, it starts looking like the thing it's supposed to. If you back project 16, it starts to look at this. It's a 256, but it's a 64 by 64 image, so you should have at least 64 projections in order to do a good job. And you see here, this is the fully reconstructed object, which I think has about, this is 16 back projections, okay? So as you get more back projections, it looks better. So that's the upshot, okay? And you can actually try that example yourself if you like. So Okay, maybe we can come back. So thank you very much. See you on Monday. Bye.